Okay, this is Chapter 4, Reactions and Reaction Stoichiometry, and we are going to pick up where we did after Lesson 1. In tonight's lesson, we're going to talk about types of reactions. We're going to review some that you should have learned in Regents Chemistry, and we're going to talk about solubility rules and how to predict the products of certain types of reactions. So our goal is to be able to predict the products of chemical reactions, just like I just said, and possibly answer a simple question about it. First thing we need to review are what types of reactions are we talking about. So we're going to talk about single and double replacement. Remember that single replacement is when an element and a compound combine and a new compound is formed and an element is kicked to the curb, basically pushed out. Double replacement is when you have two compounds and they basically switch partners. We have decomposition, breaking something down. We have synthesis, we're putting something together. And we have combustion. Combustion is when something combines with oxygen to produce carbon dioxide and water. So the first thing we need to know is our solubility rules, which you just had a quiz on and most of you did very well. An easy way to remember solubility rules is something called na, cul, no, so. So NaCl, no, so. And it's easier to learn what is soluble and then whatever exceptions that you might have. So when we talk about solubility, we're talking about solubility in water. So when we say Na, we're referring to sodium and other group 1 ions, such as potassium, lithium, rubidium, cesium, and the ammonium ion. So Na for group 1 and ammonium are all soluble with no exceptions. Then we get to the culs, chlorine. So that means we're referring to the halogens, chlorine, fluorine, bromine, and iodine. They're all soluble with the exception of silver, lead, and mercury. Then we get to the nos, which are your nitrates, but it also includes your chlorates and acetates. So nos include chloride, so nitrate, chlorate, and acetate are all soluble with no exceptions. And then you get to your SOs. Your SOs are your sulfates. Sulfates are soluble unless they combine with barium, calcium, lead, and mercury. And then basically the rest are insoluble. Your sulfides, your carbonates, your chromates, your phosphates, your phosphites, your hydroxides, and your oxides. Now there is one special case when you have your hydroxides, barium, strontium, and calcium are slightly soluble. So let's look at a couple of examples applying NaCl, no, so. So if I look at Na2CrO4, sodium chromate, I'm going to see Na, and I'm going to think it's soluble. If I think of SrNO32, sodium nitrate, I'm looking at the nitrates, which I know are all soluble, no exceptions. PbI2, so I falls under culs, not cul, chlorine, including all my halogens, are soluble with the exception of mercury, lead, and silver. So this is going to be insoluble. And iron 3 hydroxides. We know that hydroxides fall under the rest rule because it's not part of NaCl-NO-So. So hydroxides are insoluble, and it's not one of the slightly soluble rules. And if I have K2O, in this case, Na, the K falls under the Na because it's a group 1. So all group 1s are soluble, no exceptions. So this one's going to be soluble. Okay, so that's solubility rules in a nutshell. So you can either have it memorized the way you do. I tend to use the NaCl-NO-So. All right, let's talk about a review of ionic, net ionic, and molecular equations. You did this over the summer, but it does fall under part of Chapter 4. Complete formulas of all reactants and products that are written as if they were molecules. No explicit indication has been made that the soluble compounds are actually dissociated into ions. So molecular, in this context, means only that a complete formula is used. So basically, when somebody's talking about the molecular formula, they're talking about just writing an equation. So here, cadmium nitrate aqueous plus sodium sulfide aqueous yields cadmium sulfide solid. Because S, NaCl-NO-So, is not part of that, which means it falls under the everything is insoluble, and sodium nitrate. So I just want us to just really quickly review. So this is molecular formula, but let's look at each compound. Cadmium nitrate, the nitrate, NaCl-No. No, nitrate falls under the no rule. It's soluble. Okay, no exceptions. Sodium sulfide, the Na falls under the Na rule. It's soluble, no exceptions. And here, this could be soluble by either rule, either the Na rule or the no rule. Ionic is taking all strong electrolytes and show them as they're ionized. So I went over this with a couple of you. You break down cadmium nitrate. So you've got CD2 plus, aqueous plus 2. This 2 tells us how many nitrates, NO3 minus. Plus we have 2 Na pluses plus S2 minus. The CDS, notice, remember, it stays intact because it's a solid. It's not going to dissociate, it formed a precipitate. And then 2 Nas aqueous and 2 NO3s aqueous. We cross out what is a spectator, and we're only left with what participated in the actual reaction, which is called our net ionic. Again, you must learn your solubility rules. They must be memorized. All right, let's talk about our reaction paths. What type of reactions can we have? First thing you want to do when you look at a reaction is you want to determine whether it's a redox reaction, meaning Leo says Ger, there's a loss and gain of electrons, or whether it's a non-redox reaction. So let's look at non-redox first. It's usually 2 ionic compounds, and it's probably a double replacement, and either a precipitate is formed or water is formed. So you have to know your solubility rules pretty well here. Oxides, you need to memorize the oxide rules. I'll go over them in a few minutes. And then you have acid-base reactions, so titration in a sense where neutralization is occurring, decomposition. These types of reactions are basically always non-redox. Remember, in a decomposition reaction, you're usually only going to have one reactant. Sometimes you'll have two, but mostly it's one reactant. Words like equimolar, are likely to be indicative of acid-base. Words like protic or diprotic, protic meaning one proton or one H, or diprotic meaning two protons or two H's, can't spell, which is also indicative of acids. So an example of a monoprotic acid or protic acid would be like HCl. A diprotic acid would be H2SO4. Okay, they do have triprotic acids as well. Coordination reaction. This is going to be new for you guys this year when we get to that. They're compounds, and you're going to look for ammonia, and you're going to look for any of these other elements that it may be combined with. These are special compounds that we're going to talk about. All right, let's look at redox. Remember, if I have redox, that means I have a gain and loss of electrons. If you look for words that say acidified or basic solution, that is indicating that it's a redox reaction. Also, if you see any of these ions, the permanganate ion, dichromate, peroxide, and hypochlorite, combustion reactions, reactions that involve air. I talked about that. Double replacement reactions. If you if a single replacement reaction, if you see a pure metal and it's not ionized, then it will, there's a word missing, it will be a single replacement reaction. Any element, either metal or non-metal, or if something is electrolyzed. So these are two paths, and it just goes to show you how many reactions that there really are, but it may also help you in determining how to handle them. So things that must be memorized. Solubility rules, check. We've already done that. Redox rules. We're going to learn that in this unit. Polyatomic ions, check. You've already done that. Metals and ligands for coordination compounds. We didn't get to that. That's in this unit. And oxide rules. That's also in this unit. So let me change those to a different color. Check mark. So purple we've already covered, and blue is what we're going to be covering in this unit. All right, let's talk about some types of reactions. Reactions with no charges, reactions with no changes in oxidation numbers. Well, if there's no changes in an oxidation number, then you know that it is a non-redox reaction. This usually happens in dissociation reactions of salts in aqueous solutions. The word dissociation, recall, means when an ionic compound dissolves in water, the ions which compose these compounds separate from each other, enter the solution as more or less independent particles, or ions. So here I have NaCl, and it's going to dissociate into Na plus and Cl minus. Okay, we're going to cross out this one. We're not going to worry about this one right now. We have non-metallic oxides react with water to form acids. These are called an acid anhydride. So you're starting with a non-metallic oxide. So it's a nonmetal and oxygen that reacts with water. So here we have sulfur, which is nonmetal, and oxygen. That's sulfur trioxide. It reacts with water and it produces an acid, H2SO4. Now, H2SO4 is one of the big six. This is very, very strong. So it is going to, while in solution, react with water and then break down into H3O and HSO4 minus. So this is a subsequent reaction due to the fact that this reaction produced a strong acid which is immediately going to dissociate. Dinitrogen pentoxide, again another non-metallic oxide. Nitrogen's a nonmetal, it's mixed with oxygen plus water. Remember, it's going to form an acid, so it's going to form HNO3, two of them. So nitric acid, which again is also very strong, will react with water and dissociate instantaneously. Metallic oxides, opposite. So if you know nonmetallic oxides combine with water to form an acid, then nonmetallic oxides combine with water to form a base. And these are called your basic anhydrides. So here's a metallic oxide. Sodium is a metal, oxygen a nonmetal, plus water is going to yield sodium hydroxide and water. Again, sodium hydroxide is a strong base, so it's going to instantaneously dissociate because this is in water and turn into Na plus and OH minus. Here's some examples of decomposition reactions. Here you have a base. Notice what makes up the base. It's a metal, and we said before that a metallic oxide, if we have a base, it's going to produce a metal oxide and water. Because on the previous page, we said that a metallic oxide and water forms a base. So it's the reverse of what we just did. Salt containing oxygen is going to give me metal oxide and a non-metal oxide. So here I have calcium carbonate, and it's going to break down into calcium oxide and carbon dioxide gas. An acid containing oxygen. So if an acid has oxygen, then it means that it probably came from a non-metallic oxide. And here, sure, that's what happened. This produces water and a non-metallic oxide. All right, let's change gears. Metal oxides and non-metallic oxides. So we've just been dealing with a lot of oxides. We said that a non-metallic oxide reacts with water to form an acid, and a metallic oxide reacts with water to form a base. So now we're saying that a metallic oxide and a non-metallic oxide form a salt. Reactions of coordination compounds. This is going to be new for you. These are called complex ions. We'll address them later on in another unit as well. It involves adding a ligand to a fourth row transition metal and a few other selected ions. There are many different ligands, but in this course we're only going to look at the most common. So those are the most common that you should know: NH3, OH-, SCN, and CN-. The number of ligands that attach to the metal will almost always, in our case, be double the amount of the charge on the ion. This is important. Okay? So the ligands that attach to the metal will almost be double, or just in our case, always be double the amount of the charge on the metal. To determine the final charge, you add up, this is also important, you add up the total charge from the metal to the sum of the charges from all ligands. You're going to get the final charge by adding the total charge from the metal to the sum of the charges on all the ligands. Okay, so let's take an example here. Well, I'm just going to write this over. So we've got a metal plus a ligand yields, this is called a complex ion. Okay, I'm just going to put it underneath. Where was I? A metal plus a ligand yields a complex ion. And what that is it's going to be the metal times the ligand, and we have some type of subscript. And that subscript is found by taking 2 times the charge on the metal. Okay? So, let's look at an example. We've got silver plus ammonia. So when we write this, we're going to write Ag parentheses NH3. This 2 comes from twice the charge on the Ag+. So plus 1 times 2 is 2. And then you've got your total charge, which is going to be the charge from the metal, which is plus 1, to the sum of the charges from all the ligands. So here, there's no charge on the NH3, so it's just going to be plus 1. Right, let's look at the next one. We have copper plus OH minus. So copper, OH minus, 2 times 2 is going to give me 4. So it's going to give me right here a 4. And what we have to figure out here now is OH is a -1, but you've got 4 of them over here. So we've got 4 times -1, which is -4. And you've got 1 copper, which is a +2 charge. So a -4 and a +2 is a -2, which is where this charge comes from. Again, just to review, for purposes of this course, our ligands can be NH3, OH minus, SCN minus, CN minus. And sometimes, well, I don't want to throw that in there, but sometimes you'll also see water in there. Okay, again, we'll be working with some of these. This is something new, and it just takes time getting used to. So let's do some practice. We'll finish up with some practice here. Hydrogen sulfide, so H, sulfide is S with a -2 charge, so it's going to be H2S, is bubbled through a solution of silver nitrate. And silver nitrate is AgNO3. Nockel, no. So nitrates are soluble with the exception, no exceptions. Sorry, no exceptions. So let's split this up right away. Sulfides are insoluble, so we know we're going to have that. And this is going to be Ag plus NO3 minus. This is the makings of a double replacement reaction. The Ag is going to hook up with the S, but S has a -2 charge, so it's going to be Ag2S plus (2H plus NO3 minus. So let me explain what I did here. First of all, I knew that the hydrogen sulfide, oh, this is the gas, I'm sorry. Hydrogen sulfide gas is insoluble because it's a gas and it's bubbled through this solution of silver nitrate. So the Ag is going to hook up with the sulfur and form silver sulfide, which is a solid. It's also going to form nitric acid, which is a strong acid and is going to automatically dissociate. Now I just did this all in one step. You could have written H2S plus silver nitrate yields Ag2S plus nitric acid, and then broke it down in the next step. So let's get rid of our spectators. NO3, NO3, and that's it. Because this was a gas, it's going to stay intact. So then my net equation is going to be H2S gas plus Ag plus yields Ag2S solid and 2H2 plus aqueous. Okay, let's check out the next one. Concentrated 15 molar ammonia solution. So ammonia is NH3. Is added in excess to a solution of copper 2 nitrate. Well, as soon as I see nitrate, I know it's going to be soluble. So I'm going to separate this into Cu2 plus and 2NO3 minus. And you could even write this over here on the side before you do it. And that's going to form what? Well, right away, well, not, you should recognize this right here, NH3, as a ligand. So a complex ion is going to form with a metal and a ligand. Keep wanting to say ligand. So Cu, and we've got NH3, and the charge on the copper we know is +2, so that means that we're going to double that and make this a 4. So let's see what we have going on here. The NH3 has no charge, and the copper has a +2 charge, so the net charge is just going to be +2. And then we're going to have this 2NO3 minus. So what's going to cancel is this, and our net reaction is simply going to be the NH3 plus Cu2 plus yields the Cu NH3 4 plus 2. Okay, next one. Equal volumes of dilute equimolar solutions of sodium carbonate. So sodium carbonate, I'm just going to write this down over here, Na2CO3, and hydrochloric acid are mixed. Well, let's look what we have. We have a Na, so we know this is soluble. It's going to split up. So we have 2Na plus CO3, 2 minus, plus we have a strong acid, so we know that that's going to split up. It's one of the big 6. And we're going to form HCO3 minus. Now you might be wondering, this is a tricky one, why didn't I form CO3, H2CO3, and it's because of this word right here, Equimolar Solutions. So that means my mole ratios are 1 to 1. So if I have H plus, then I can only have a 1 to 1 ratio, so it's going to be HCO3 minus. And then my Na plus Cl minus 2Na plus. So this is going to cancel, and this is going to cancel. So my balanced equation really, or my net equation is CO3 2 minus plus H plus yields HCO3 minus. Okay, let's continue on. Dilute acetic acid. So we've got HC2H3O2. That's acetic acid is added to solid magnesium carbonate. So we've got MgCO3 solid. So what's going to happen here? Well, there's going to be some separation, but not much of the acetic acid because it's weak, so it's going to barely ionize. But we will have some of the H hooking up with the H2CO3, making some carbonic acid plus Mg2 plus and C2H3O2 minus, the acetate ion. And what's going to happen is the carbonic acid will also dissociate. It won't stay long as carbonic acid because carbonates always break down into H2O plus CO2. So you might want to put that carbonate turn into CO2 and H2O. Sulfur trioxide, SO3, gas is added to excess water. So you need to think about what we've got here. We have a non-metal oxide, and we know that a non-metal oxide plus water yields an acid. So you're going to have H2SO4. But remember that H2SO4 is one of the big six. So it's strong. So it's going to dissociate into HSO4 minus and H plus. The last one, powdered magnesium oxide, is added to a container of carbon dioxide gas.